Okay, so I think time is pushing on a bit. So I'm going to talk about ctypes, and ctypes is a Python library. I'm going to talk about ctypes because it is a Python library that allows you to call C functions directly. So let's have a quick look at what ctypes is. It's a foreign function interface for Python, calling C functions from Python. If you've written any Python modules or extensions, you'll know that you can write C code that embeds in Python in order to produce reasonable quality implementations of libraries that talk to native C implementations of things. The ctypes infrastructure differs a little bit from the extensions in that it is working against non-Python aware functions. So this is a way of calling directly into shared libraries that you have implemented functionality into from Python without having to write any boilerplate C code around them. There's a little bit of Python boilerplate around it that we're going to have a look at later on. And how does it work? So what ctypes provides you is a set of basic types, like things like integers and doubles and floats, arrays, structures, and you have just the basic concept of a structure and a union and an enum. And on top of that, what you do is, as an application, you need to combine these individual types into more complex types like particular structure instances, enums and unions, arrays, and all the rest. And given this definition that you provide to the Python ctypes interface, what it does is it can work out the layout of those individual structures as they would be produced by the compiler. And it can then provide a wrapper that allows you to build the stack that as it would appear when that function is called from another C function from Python. So that probably sounds more complicated than it actually is to implement or to use. So just in terms of what we use it for, we use it mostly here for writing tests. So we have a huge infrastructure of Python code that we use for implementing network topologies, sending packets around the network, that kind of thing. And internally, we will call directly into C code from the Python functions in order to make sure things are behaving correctly. It also means that if you actually have a failure in a test, you end up in this like nice little REPL-based environment where you can interrogate your program for, call functions, see what structures they give you back. And it's just kind of this interactive interface you get basically to your C code. Anyone got any questions about that? Does anyone actually use ctypes before at all? One or two? Okay. So it'll be relatively new for you. Yeah? So the question is, does it support C++? So kind of. So depending on the types that get generated. So for example, if you generate types with multiple inheritance, it's probably unlikely to work. If you generate code that's basically got a C-like linkage, it will probably work. I haven't actually tried, say, calling member functions through a virtual function table. But for most things, the calling conventions are going to be the same. And I'll go through how we actually do that a bit later on. We'll kind of cover a little bit more detail. Yeah. To Swig. So Swig, from my previous experience, is something that will take, I don't think Swig exists for Python. I think Swig tends to work more for compiled languages, in that you will generate, say, calling stubs for, say, Java, from C to Java, or from Java to C. But it's, because Python is an interpreted language and you really have to run the code in order to generate the structures that something like Swig would need, it's somewhat different. So it's probably the closest thing that you get to Swig from Python. So it's inherently different because it's an interpreted language, but it's conceptually similar. Okay. Okay. So just to give you a basic example of how it works, this is a structure, obviously, and this is a function. And the intent is that we want to call this function here from Python. So in order to do that, Python has to be aware of what this structure looks like, how it's laid out, and it has to be aware that this function exists somewhere. And it has to be aware of the return type of this. So it can pass this in and return something from it. Make sense? So here's the boilerplate that we use from Python to call this. So this is just really importing everything from ctypes. The cdll will basically do a DL open on the library if you're using Unix, load library, whatever it is in Windows, I forget. But this will just really give me a handle on the library. And this is pretty much just a very thin wrapper around whatever the operating system's model of a shared library is. Then what I have to do is declare some kind of detail about the content of the structure that I want to pass around to this function. So this, you can see, is pretty much just mirroring what's over here. So I say that I have a field. So I've got an array of tuples that says that the first field is I, which is a cint. This is a ctypes primitive. I have a type, or a field C that is type ccar and ccarp. And for the actual function that I want to call, I have what's the equivalent of the prototype for it, where I say that this function has this type, which is C double in return. So the lib here, you can see I'm accessing this field directly off it. So through the magic of Python's getAttr methods, what it's doing is it uses DLSym or the equivalent on Windows in order to find out where that symbol is and generates a Python wrapper around that object. So by doing this, I'm basically telling ctypes, in order to call this function, some function, I need to pass it a pointer to some structure. So these are all the kind of the building up the primitives that ctypes provides you with in order to generate enough information to call that function. Okay. And then once I've actually generated this kind of boilerplate in order to say, here's my header file that has structure definition and prototypes in it. Now I can actually just use this type directly and construct an object of that type by just passing the arguments into it one by one for each of the fields and declared in order here. So this creates an instance of a type sum structure embedded in a Python object. Okay, not clear? Okay, so once I've done that, I can directly call this sum function from the library, and I can pass this sobj thing by reference. So this, because this is an actual object, I need to kind of say that I'm basically taking the address of it by doing this, right? And then I can basically print out the results. So you can see what I've done here is I've passed in this 3Q and hello world, and print out the contents as they were passed in here, change one of the values, and return something. So the actual output from this, from basic ctypes program, is that we get what you would expect. You can see the values passed in from Python, and you can see the values coming back from the C function available to Python.
See, you instantiate some structure with the hello world. Does it have to be binary?
So the question is, does it have to be B hello world? So this is, if I do this without the B on it, I'm going to get a Unicode string, which I'm not even sure how Python represents them. So because the actual function itself, or the actual structure, has a char star, it needs to get a raw char star for it, right?
It doesn't transparently convert strings.
I can't remember whether it doesn't in Python 3 or does in Python 2, but it doesn't work normally. I needed to put that in. My initial implementation was not to do that, and then I worked out I needed to do it. So no, it doesn't do too much automatic conversion of things from one to the other, because what tends to happen is at times it will tend to misinterpret, and it might be right 90% of the time, but then 10% of the time you can do nothing. So okay, this is the basics of how the whole thing works. So wake up, computer. Okay, so this is the code from the original thing, and the real problem we have here is that all of this is really just a replication of what would be in a header file, or what the compiler sees as it goes by. And when I started here, we were kind of using this C-type stuff, and I think it was a relatively new thing for us at the time. But we were manually generating all of this for all of the structures that we had. So in order to change something, if I change a structure in C, I would have to go and modify this in order to put a field into it. If I wanted to change the return type of a function, I'd have to change this here. But I mean, we had tests that would verify that particular things had the right size and the fields had the correct offsets and everything. But it was still relatively error prone. You would generally find after the fact that you changed something that there was something you had to do in the Python library in order to fix it. So we're kind of thinking that it's repeating the C source with a different syntax, and can we get the compiler to output something for us that we can use in order to avoid the overhead of writing these by hand? And it turns out that it already does. So I previously gave a talk here where I talked about Dwarf, and Dwarf is something I like to talk about a bit. Dwarf is the debug information that's stored in ELF executables normally, and I've taken the dump file from this particular library that implemented that function here. And we can see this big mess of information here. Now, I'm not going to go through the entire detail of this, but we can just have a quick look at what it actually did with the types that we're interested in. We can see that we have this DW tag subprogram. So this is saying that we have a function, basically. And we can see the attributes associated with this debugging information entry. And it says we have a name, and we have a type. And this type here, this 5.2, this is an offset into this table here, so we can look down. And this is a base type. And it's saying this is the name of it's double. It's encoded as a float, and it's 8 bytes wide. So this is telling us that our function returns a double. This is the type of the function. It also has formal parameters, so we can see that it has a parameter called s, right? And s has this type 59, 59, and 59 is a pointer type. We can see here 59. Then the pointer type, and then it's a pointer to one of these. And we can see if we look at this 5e that we have this thing, it's a structure type. And this is the thing we're actually interested in creating and passing in. So we can see the structure type itself as members. And these members are things like this I field, this C field, and this S field, right? And if we trace to this, we'll see the same thing. This will be a pointer to a car, right? Any got questions about that? No? Okay. So what we did was we basically took this information that was being generated by the compiler anyway, because we need to have debug symbols in order to debug things, and we just parse it out. So we have a library that parses out the debugging information anyway. And then given that, we were able to generate enough code to call the ctypes functions directly without having to write that boilerplate header file style stuff. And when my computer wakes up, we'll have a look. Okay. So we can use code like this, which just imports ctype gen. We give it the name of a shared library, which was the function that, or the library that our functions are contained in. We can actually give it a list of ELF objects in order to search if there's information in multiple objects. We give it the name of the Python module that we want to create. And then we just list the types that we're interested in. Simple examples, I've only got one type, which is this sum structure. And I give it a list of functions that I'm interested in interrogating in some way. And given that, we can generate this. And this is coming out directly from the generator. And it has this basically a forward declaration of the type. Then each of the individual fields, you can see that we store things like the native size, which is the size as it came from the compiler and from the debug information. And we can verify that that matches up with the size that ctypes understands the type to have. And then the individual fields in it, which is what we saw before, we just have to declare them each in turn. And then we have this set of offsets, which says that for each field in turn, this is the offset that it should be within the object. And again, we can use this to actually verify that the type that we've generated from the debugging information matches pretty much exactly with the type from the Python ctypes interface. So this was really just to validate that the changes that we made were still getting the same test that we had before that. Okay, and we also get this decorate functions function, and we can call this on a loaded instance of the library to decorate each of these functions with their result type and argument types. Clear? No? No. Okay, so in order to modify the way, in order to let Python, the Python interpreter, the ctypes module know how to call the function and what arguments it takes, it needs to modify this loaded wrapper around the DLL. So whatever DLL you've loaded, each of the individual functions that are defined in that DLL, you can access as fields in that lib object by name. And that the getAttr thing in Python will basically cause that to get DL opened, or the DL sim to be run on that name, right? But in order to call the Python, in order to call the C function, the Python code needs to understand the return type of the function and the arguments to pass into it. So it'll convert the Python objects into things on the stack that the C function will see as being C objects, right? But it does.
In the previous example, this just wasn't inside of function called decorate.
Right, we did this inline. We did this inline in the code. So if we go back really quickly, okay, we have it here. So this is what I wrote down myself, and then I wrote this code to actually fill in the return types and the argument types, right? So now what we have is the same thing, only we've got a function for this. So for a single function, it seemed a little odd, but I mean, we could, for example, pass in, we have code where we'll pass in like hundreds of these, right? So this is the functions that we're interested in looking at. So I want to call this from Python at some point. So we may have a library that has hundreds of functions in it, and we may have this full list in here, some regular expression to say this is the ones to pick out.
You have to explicitly invoke decorate functions.
when you use the interface, you'll have to call decorate functions, and we see the actual code that gets the comparison code between them. So this function types thing here is just something that we needed for something else. It's not really too relevant. But so this is the main kind of work that we need to do. We need to generate the type definitions and the argument types and return values for the individual functions we want to call. So this lets us go from having an implementation that looks like this to something that looks like this. So what we've done is we've really just gotten rid of all this boilerplate and replaced it with just loading in the DLL and calling a function here. And we get all these definitions from this kind of generated code that we've already done. All right. So again, this is kind of, as well as changing the size of the code, we have all of these automatic checks now so that we know if we change something in one of the header files and the Python gets generated at build time. So that's not going to need to be changed. If you change the return value of things, so for example, if I change the return value of this sum function from a double to be a float, without changing anything here, what I would just get is garbage back from the call, because it would the Python interpreter would try and interpret the 8-byte value as a 4-byte value and get it completely wrong. And again, as we use more and more types, the savings get higher. So I mean, as I say, we might have like a few hundred functions defined by the generator and a few hundred types, and they all get generated, and everything gets loaded in by these two lines. Right? Okay, so that's pretty much what I wanted to say about the way this works. Okay.
But still, it doesn't seem, it doesn't be a transparent layer for shared content. Because say you have to call by ref, for instance.
There is a certain amount of manipulation that you need to do with this. So I mean, really, what happens is you don't have things like an ampersand operator to take the address of something. So in the same way that this is not like a header file, it's a little bit syntactically different. I just have no way in Python of representing this with anything other than a function call. I can't define operators in Python that do and. So you do need to be relatively familiar with the ctypes infrastructure and Python.
So that's a function that takes by ref.
So this is basically the ampersand operator from C.
What is the signature of the function?
It's Python, so it doesn't have a signature. It just takes an object and returns another object. And it's all hidden in ctypes, so you have no idea what they're doing.
You're calling the star there on obj.s.
Yes. What was this coming back? So this is this here, right?
Yeah.
Okay, so I want to. So this is a C carp. So this is a ctypes type.
So it's the same thing in C.
It's not an str. No, so you can do things like poke at individual parts of it, for example. So it's mutable, right? And you can do things like take the address of individual fields. You can find its address in C, so you can pass its address some other way, right? Another question?
Final question to me. It was, is there anything that makes that kind of introspection of types not upstream? You look at the Dwarf stuff, presumably there's equivalent stuff that can run on.
I'm not sure what you mean by non-upstreamable.
But ctypes itself do that type introspection.
So I mean, this could be added in. I mean, but in order to do it, you need to introspect the types in C. So in order to do introspection in C, you're going to need some framework to do it. So standard C program is not going to provide you with the way of accessing individual fields or enumerating fields in a type.
I mean by examining the Dwarf.
Examining the which? The Dwarf? ctypes could provide that, but it doesn't. So that's why we added it.
Any reason for that?
Lack of time or interest by the parties involved in writing it, I assume.
Does that mean that only works for debug code generator or not?
So you need to generate the symbols from the debug code, but if the symbols, you need to generate the debug information for the debug code, but that doesn't necessarily have to be the same binaries that you ship with. So for example, if you build, I mean, the builds that we do and the builds that say happen for something like Fedora, you will do optimized builds that will still generate debug information that you will store in a separate file. So you can install a, if you've got a foo.rpm, you'll have a foo i686 rpm, you'll have a foo-debuginfo.i686.rpm, which will include all the type information. Just because it's optimized and the code paths are shorter, you still need the type information in order to provide the ABI from compile unit to compile unit.
Do you ever consider using something like the Clang AST stuff?
So you could potentially use the Clang AST and do something similar to this. I didn't have experience in that. The other thing is we don't internally use Clang. We could have added it in as an option. Again, the Dwarf thing is kind of probably more universal than Clang is, and at least for us. And the other thing about this is that it would work for other languages as well. As long as you produce Dwarf debug information and you have an ABI that is relatively like C, this should work. So it does, to some extent, work for C++. There are other implementations that actually would parse header files and do stuff like that. The only ones that I actually looked at in any anger tended to have big problems with header files with lots of macros in them and didn't work well at C++. So, I mean, you don't want to re-implement the parsing of the language. I mean, Clang would give you the AST all right, but this was somewhat simpler. And also, I like Dwarf, so I know more about that.
I think if you did use the AST, you'd end up generating some Python, right?
Yeah, you might generate Python.
Find that at the end of the day. Because this, all that Python has to do is look at the file.
So I don't need source to do this either. So I can do this once I have debug info. So I have an example later on if I get time to do it that we can have a look at how this works for something more complex.
You ever have to deal with same C structure having different layout depending on whether it's a 64 or 32-bit or diagnostic?
Right. So we would have that issue. We would have to have separate modules for 32-bit or 64-bit. Right. So even if we were not using the Dwarf information, we have the same problem. The layouts are potentially different. So they may be similar. They may be identical because I mean, if you're only using kind of one side, if you're using types like cint, then there's a mapping directly to a Python type like C, like int, or between cint and Python to int and C. So as long as there's a direct mapping between all the types that you use, that's fine. But then you have things like, I don't know, well, just I know, for example, there's bugs in it that don't work well with bit fields, for example, because the layout's different in 64-bit and 32-bit, and you have to deal with things like that. I mean, so I would err on the side of caution and generally build 64 and 32-bit.
Local Linux is 64 or 32-bit depending on the build.
These days, it's always 64-bit, but I mean, in maybe if I had an old compiler or a different architecture, yes, I would have to change them. But it would still be it would still map from long to C-long and Python, and C-long and Python would be the right type for the architecture that the Python interpreter is running as.
Is there any issues, or does it support things like calling conventions, or is that something you don't need to worry about?
For ctypes, it generally just assumes the standard calling convention of the architecture you're running on. So I think so in Unix that makes no real difference because there's one API for a particular platform normally. For Windows, there may be some way of decorating a function with it to say it's standard call or C call or whatever. I'm not sure.
Again, Windows, that's only an issue in 32-bit and 64-bit. There's only one code.
Sure, right. So I mean, this is probably going to work in 32-bit as well, but it probably assumes a certain calling convention. I'm not sure. Or there's probably some wrapper you can put around the type to say it's a standard call. I don't work with Windows, so I'm not quite sure.
I wonder what happens if C code spawns threads or forks processes.
Bad things. So, I mean, you can write Python code that interacts with C code that creates threads. It will work to some extent as long as you're very much aware of the problems that you're setting up for yourself. So there's one particular artifact of all this that, again, if I can get to it and see, where in some ways the interface does break down a little bit and it just kind of has to admit that something's gone wrong and you may need to be careful here. Okay.
Do you have them or support things like re-entrancy back into Python, like callbacks? I don't know if you do that, you're going to.
I'll come to that. Okay. So, yep, another question. I can't hear the question. Sorry.
Question about clearing C code that also C code that implements something that's from Python. I think that's how TensorFlow actually.
So within if Python wants to do anything that deals with the operating system, it's going to make a system call. It's going to have to go through C code to do it. Yeah. Sure, and I mean Python has this infrastructure with its the giant lock that it uses around everything in order to make sure things are thread safe. And we do internally here have services that are running Python binaries safely in a multi-threaded environment. It's not that unusual to do it, but there are obviously complexities if you call a C function that goes off and does things that complicated like creating threads. All right. So this is kind of what we kind of started off. The original kind of presentation is just going to be about this. And we kind of combined a few different things together to produce something quite interesting, which comes back to the question that we had about callbacks. So what we started looking at was doing mocking with this. So if we have a C function that we want to test, which is this entry point, and it calls a callback function, or it calls a function within it, f, not necessarily a callback function, it just literally calls this function. And this function does I/O, or some other complicated operation, then we can't easily mock, or we can't easily test this function without actually mocking out this. So, I mean, we could do this at compile time in some way, but what we decided to do is use the infrastructure that we built up and some hacks with the way the linker works in order to be able to do things like this. So what we can do is we can say, import the CMock package. And what I want to say is I want to mock this function f in the library. This is one of these functions we looked at earlier on. This is just a function implemented in this library. We pass it in the library as well. And really what happens now is that if this function entry calls f as part of its work, using some of the linker structures, we can make it actually call this instead. So we can actually have it automatically, unknowns to the C code, end up in Python, right? So this is just restating what I said. So we want to basically call mockdef rather than f from our C code. So here's an example. Well, let's start off first of all by having a look at how ctypes does callbacks. So the question before was basically, can we call from Python into C? So ctypes does provide us this ability in that it allows us to take, say, a function like this, well, say a type definition like this, which is a really simple callback, take it as an argument to a function. So in order for ctypes to do what it does, it needs to be able to support this. And this is just a basic example of how we would do it. We can open this library, call our decorate function thing yet again, and define this operate function. And then what we need to do is we need to kind of, because this is a Python function that hasn't got any real type information associated with it, we use the type that we generated from this as a constructor to create code that we can actually run in the Python or in the C code. All right? I'll start that a while because it's doing a lot. All right? But this is just generally how ctypes works for calling functions from the callback from C to Python, right? But because when we have functions with external linkage on the platforms that we're interested in, they go through this linkage table in order to actually resolve the function. So for example, if I have a piece of code, if my function entry from earlier on calls a function f, if that f has external linkage, it will jump through a table in order to get to that function f. So if we can find that table and find that function at the table, then we can replace the function pointer in it that's pointing to the actual implementation of f in the C code with whatever this actually generates. So all we need to do is actually just grab hold of the pointer that this actually generates, make sure this object stays in scope long enough, and we can call any function we want from, we can have our entry function in C call whatever we want from f, and we can get it to call this generated Python stuff. All right? Any good questions on that one?
You have to put the address back after you finish.
If you want to, you can. So,
Okay,
I mean,
so
this is going to be,
yeah, for mocking you.
this is for a test. So generally, you're not going to use this, say, for example, in a re-entrant environment where things are actually also calling f for other reasons, right? You can enable and disable the individual mocks if you want, but the reality is that your tests are probably going to be short-lived enough that you really won't be doing that often. I mean, it's a very specific environment that you're running in. This is not going to happen in production, right? Okay, so again, we can hijack that global offset function or global offset table from the linker in order to implement what we want. Okay, so I'm going to try and just give you an example of how this works. Can people read that at all? Is that legible? Okay, so what I have is, this is my main program, which calls function to test and prints the result. And if I look at my test code, this function really what it does is it has a buffer. It's not particularly securely written, but it basically prompts you for a number, gets a line of text from the user. If it gets end of file, it breaks out, and then it just converts that string into a number and adds on to this running total, right? And then eventually it returns the sum of all of the numbers that you typed in. So just show that it works. I can type in 10, 20, 30, 40, 50, and it prints this out, right? So I can test by hand that this does what I expect it to do. My problem, of course, is that if I wanted to test this in isolation, it's kind of tricky. So what I want to do is I want to set up a Python test that what I can do is I can call this and I can mock out this and this, right? So if I look at, my window's just slightly too large. If I have a look at, say, ctype. So this is this ctype.py, which generates the type string, right? I have a little module here, paths, because the libc library location changes from time to time. So this is just something separate to stop cluttering up the output. But I can see from libc, I generate libcgen.py. From the testb shared library that I generated, I generate this. And within libcgen, I want to override this function and this function, so I need to mention them. And I also want to call this from the testb library, right? So I can just build the ctypes information. And again, it's just generated this for me. So I want to actually I want to change fgets. Just the way the debug information works, it actually isn't called fgets as far as the debugger is concerned. It's called IO fgets. So there's a little complexity in that, and the same for puts. And then this is the same thing for the testme function. So there's nothing really in the testme other than just the definition for this function to test. It's return type and it has no arguments, right? So given all that now, I can go. So this is the actual test itself. So I've import a few of these things that I've looked at before. I need to open this libc DLL. I open the testme DLL, call the decorate functions on both of them. And at this point, I can actually mock out libc's fgets function with this. So what this does is it just has a running sum, and it'll count to 10 and return 10 for the first 10 times, and then return a null pointer, right? Because of that weirdness with the linker name, we actually have to hint to say what the name of the function is here, and also here. But other than that, it's pretty much as we saw before, right? And then at the end, all it does is just call the function, so you print out what it results in. And again, I just run that, and I get this output here, right? So I've basically done this without any I/O or needing anything from libc. I've stubbed out the libc functions. This is coming back to the point we made earlier on about sometimes strange things will happen. So because this function returns a character array or a piece of memory, and the ctypes implementation doesn't understand that it's basically either a pointer to this or null, then it has to really allocate memory for this at this point. And because there's no other way of interacting with the system at that point, there's no other option but to just throw it away or leak it eternally, right? So that's just an example of using this in order to kind of implement mocking of a C function from Python without having to actually write any C code. And that's me done. Any more questions?
Do I have to?
Do I have to export the function to Python using the same framework to mock it? Can't I just mock fgets by name?
I don't quite get the question. You're talking about the thing that had to do the IO underscore thing in front of them?
Yeah.
So that's just an implementation artifact of the way the C runtime works and the way it links it. I could probably improve things in order to not have to do that. It's just that the debug information has a list of entry points that have names associated with them. And there's a separate table of exported functions and the dynamic symbols that you need to link against. And it just so happens that fgets has a weak reference to underscore IO fgets. So in the debugger, you just see the mangled name. In the exported table of symbols that you can call, you see the unmangled name. You wouldn't normally get that mostly if you're developing stuff yourself. It's really kind of there because the libc is old and it has lots of complexities that are to do with historical reasons, and you need to be able to override fgets for some reasons and whatever. But it's for most cases you don't need to actually distinguish between the two names. I just left it in because it was a complexity I came up with, and I thought I'm going to show that it's actually there.
And can I do that with functions that are in the same compile unit? I mean, do I always?
As long as they're externally linked, then generally yes, yeah. Because the linker or the runtime basically guarantees that if you override it with something else, you'll get the overridden version. So this is where you do this LD preload trick where you can kind of say, I want to override this function, but a shared library, and just LD preload it. But yes, generally, if there's an external linkage on the function, the assumption is that you are able to override that with some other implementation. I mean, if you have static functions or things get inlined, you can't do anything with it. This works using this global offset table. So one of the problems with the global offset table is that it only exists for shared libraries. And I mean, we need shared libraries here anyway, but it only works for position independent code. You can actually build 32-bit non-position independent code and you put it in a shared library and have the linker do all the complexities later on. And in that case, you don't have a global offset table. And there is actually a hack of an implementation. And what it does is it just scribbles over the start of the function rather than actually the entry in the table. So you find the code and just scribble over that, and that'll do instead. That only works as long as your function takes up more than 5 bytes, and it only works in 32-bit. And in that case, you could probably get it to work even for static functions as long as you had the debug symbols and they had functions that were bigger than 5 bytes. Yep.
Yeah, I'm left profoundly confused with this last mocking example. So what would happen if you try to mock a standard C library function that is also used by the Python runtime? Would it not?
Bad things will happen, yes. So the question is, what happens if I mock functions that are used by other parts of this Python runtime? Yes, things will go horribly wrong. So we would generally use this for mocking out things that we implemented ourselves.
But how do you know that Python runtime is not using the puts and gets that you can mock
My code ran.
from the same?
Because my code ran. I mean, this is literally just an example. I figured I'd show something that did something relatively significant that I could get rid of. But yeah, I mean, this is not going to, if you call something that Python uses directly, you're not going to get anywhere. But to be honest, it's only in the path from the ctypes function call into the function that matters. It's only in the call stack between, when you call it. I mean, if you leave the mock, you can disable the mock later on if you want.
So you do restore the original function at the end of each and then of the scope.
You have the option to disable them, yes. But I mean, yeah, if you leave it running long term and you've got lots of stuff from libc stubbed out, it's going to go horribly wrong. Then. So I would tend to avoid stubbing out things that are implemented in anything that Python links to.
Let's try mocking malloc.
In Python, nice Python implementation of malloc might be nice to see.
Jesus,
Garbage collection? Well, Python barely has that, so.
I have one question about this. You use this to generate the to generate the test for the C code, or you just want to generate the interface for Python users?
We're using this to test C code, so we will basically take an existing implementation of whatever piece of code that we have internally, and if we want to actually unit test individual functions, we use ctypes to just poke at call functions and see if they return the right values.
So why are you particularly interested in using Python to generate all the test cases? Also, you are manually actually writing the test case.
Or we have to manually write the test cases, whether it be in Python or C. We could write them in C, but as I say, we do have an infrastructure of Python code that we use for doing things like setting up topologies and network connections and that kind of thing. So we will create, say, a namespace, a Unix namespace, and say create network links in it. So that we'll have virtualized network devices that we can plumb together within Python. So we could do that in C, but it's kind of messy. So we're using Python in the same way, I suppose, like a DevOps system would work on it. We use it to actually plumb together machines, which may be real machines or maybe virtual machines. And then while we're in that domain anyway, we just have the ability to call Python functions. And I say it does give you this REPL, so you can actually sit in the command line and call your C functions without having to constantly, edit, compile, and link.
So from your experience, do you think the Dwarf information is totally enough for your work, or it's still missing something?
We replaced a pile of Python code that was maybe grew organically over the space of years with about 2,000 lines of generated code without any major problems. So it's adequate for everything we've used it for so far.
Okay, just for me, it's kind of like a source-to-source compiler, but you were directly dive into the low-level Dwarf information. That's surprised me, but yeah, if it works for your work, I guess it's a good thing. Thanks.
Okay. So I mean, the thing is, you're not trying to parse a language. It's really just the ABI you want to meet. You're not trying to interpret the entire output of the entire code suite of the C code. You just really want the interfaces to it. And by
you can simply just add an option to the compiler and say, I want to generate all the interfaces for the Python, and it can generate exactly what you want.
I need to I need to modify the compiler then, though. I mean, I could get the compiler to do this for me, but I mean, compiler engineering is a harder job than parsing debug information.
So just a question on the Dwarf stuff.
Yeah.
Does that have more information about the types of the parameters than, say, if you demangled function name?
If you were writing in C++, you could demangle the function name or the names, and
get the same, or would you get more in Dwarf or less in Dwarf?
So the question is if I get more or less information about the function prototype, the function arguments in Dwarf.
There's no
I'd-
overall space, so if the manual, you know,
Yeah, sure. Yeah.
Right,
It's fair, but I know you wouldn't get return types in the Mango thing.
I think they're probably, one thing you might be different, I'm not sure about the ABI, but you might find that if you have type defs, you get the type defs rather than the underlying types. I don't know what the Mangler does for that. So if I have a type def int size t or some size t int, then I will get the size t, I won't get the int. I don't think the demangler does that. Okay, as I say, I'm not sure what the ABI does. We get at least as much, I think, in the ctypes version. I mean, again, it's enough. It's enough to allow things like GDB to call functions. It's enough to allow, calling functions from debuggers and that kind of thing, and examining structures and debuggers, and you expect it to work. So,
You don't code them.
oh, we can do that too. Yeah, we can dub core too. Yes.
But normally you don't code them.
Right. Sure. I mean, when you're playing around with the stuff, you would generally kind of cause the odd core here and there. Yes. Any more? Okay, no more questions. I think we're done. Thank you. So there's a link there to the actual implementation. This is actually available now on GitHub for the Arista Networks organization. And there's a link to the slides there as well, which I'm sure the C++ user group guys will send around. Thanks.